and instead we're going to talk about the relationship between multiple cameras, specifically starting with two cameras. And that's going to eventually get to the point where we were talking about in stereo, that if you know the relationship between cameras, that you can know where the epipolar lines are. So basically, if I gave you some corresponding points, you should be able to solve for the relationship between the cameras that will allow you to find those epipolar lines. And that's what we'll be doing over the next 3 or 4 lessons. Welcome back to Intro to Computer Vision. Today we're going to start a section that's really on mapping from across multiple images, image to images. And so I'll refer to it as N views. Mostly we're going to think about 2 views, but a lot of this stuff extends to having multiple views. Today what we're going to do is we're going to be talking about image to image projections. Because last time we talked about calibration. And calibration was all about going from the world to the image. And we made a stop. We go from the world 3D coordinate frame to a camera 3D coordinate frame, and then we do a projection from a 3D camera coordinate frame to a 2D image frame. And we built that M matrix, and we talked about if I gave you 3D points in the world and 2D points in the image, how you could figure out what that relationship is. For the next several lessons, we'll be talking about mapping from one image to the other. And this is going to be important both for stereo and for other applications where you have multiple views of the same scene. So here I have I think this is a figure from Forsyth and Ponce. Maybe it's from Salisky. I hope their lawyers aren't watching. It's somebody. And basically it talks about how you can transform an image. And so on the bottom left-hand corner you have a square, and you can see you could just translate it. They call it Euclidean, but that's just a rigid transformation where you have the rotation and translation. You have similarity, affine, and projective. And we're going to talk about each of those in terms of the mathematics. So let's take the simplest example. So the simplest example here is translation. So we have an X, and by the way, in this cool little figure, sort of the original X and Y is the green box. And we take our X and we just add some translation vector to it. And we saw that it was an easy way to describe this using homogeneous coordinates, where we just do X, Y, and 1. We add a 1 to the end, and then we can just have a transformation matrix here, which is just made up of an identity plus the translation vector that we had from over here. And to keep the whole thing in homogeneous coordinates, we would just say, we would make instead of a 2 by 3, we would make this a 3 by 3, so that 0 vector now is on the bottom row, and what we would do is we get from one homogeneous vector to another. Okay? So that would be translation. By the way, because these are now just matrix multiplications, we could chain these transformations. So we also have talked about projective transformations. And remember, for 3D, we said that we used 4-length vectors, and we had 4 by 4. Well, for 2D images, it's just a 3 by 3 matrix applied to a homogeneous coordinates. So here I've written this as I have an original vector x, y, w, w being the homogeneous coordinate. I apply my 3 by 3, I get a new x prime, y prime, w prime, and of course to go to the non-homogeneous I have to divide through by the w prime later. So using this sort of general framework, we can look at all of the transformations. So let's go back to translation. So translation in this framework is just the identity matrix up here, the translation there, the 0, 0, 1 there, and we go from x, y, 1 to x prime, y prime 1. In fact, we didn't have to do any division because we maintained that 1. And that's drawn with this cool little picture here where we just take this square and we can just translate it around. Nothing changes orientation size. And translation preserves the lengths and areas of objects, so as I move them around, the angles stay the same, even the orientation stays the same, and because this is a projective transform, lines remain lines. And lines remaining lines is going to be key to everything we do for at least 5 lessons. Well, 4 or 5 lessons. All right, so that's translation. A rigid body transformation can be represented this way as well. It's called Euclidean or rigid body. And now, instead of having just a pure identity matrix, we have this rotation matrix. So we can rotate in the plane, and we can translate. So we have 3 degrees of freedom here. And again, we've maintained a rigid body, so lengths and areas are all preserved, angles are preserved, lines are preserved. But of course, the location and the orientation can change. Another one which people don't think of quite as much is what's called a similarity transform. In a similarity transform, we have translation here, the rotation by the thetas, and you'll notice everything is scaled by A. Okay, so that's an expansion, that's a scale. So there's translation, rotation, and scale. So how many degrees of freedom of that? 4, right? 2 for translation, a rotation, and a scale. Now, one that we use actually a modest amount in computer vision is what's referred to as an affine transform. Okay, and an affine transform, you'll see that we have 6 degrees of freedom here, and I've just written them as a linear transformation, A, B, C, D, E, F. Okay, and again, we go from xy1 to x prime y prime 1. And what an affine transformation can do is essentially map, and we'll look at this later, any 3 points to any other 3 points. All right? And what you do is you're essentially now being able to translate, rotate, scale, and skew the image. And there's skew in both directions, so there's 6 degrees of freedom. You still maintain parallel lines, so the edges of this square become an edges of a parallelogram. Okay? And ratios of areas remain the same. So if I had one area here that was half the size of the area to the left, then its transformation would be half the size over here. But the area itself can change right through scaling. All right? And again, lines are mapped to lines. Notice that we don't have to do the division still. Remember, these are homogeneous coordinates. So here I wrote it instead of with W, but with S's, right? So it's full homogeneous coordinate system, which will go from the homogeneous xy1 through a linear operation to a scaled version of the new x prime y prime. All right? So the full transformation is referred to as a general projective transformation or a homography. And a homography still maps lines to lines, because remember we talked about perspective transforms always maintain lines. And things that are inside of each other stay inside of each other. But this is what's typically sometimes referred to as perspective transform, right? So the idea is if I had a plane and I was very close to you and I tilted it this way, and we'll do more of this later, the edge that's near you will seem longer than the edge that's farther away from you. And we'll prove later that the transformation of a plane can be represented this way. Now, of course, because this is a homogeneous transform, I can scale everything by a constant and it has no impact. So I can make this last degree of freedom be a 1, right? And I'll get a slightly different W, but it doesn't matter because I'm going to divide everything through by W anyway. So that 8 degrees of freedom, that's the full homography. It's referred to as the homography. Now I want to do a little series of quizzes that relate essentially the transformations to points. So here's quiz number 1. Suppose I told you the transformation from image A to image B is a pure translation. How many pairs of corresponding points would you need to know to compute the transformation? So I say pairs of points, meaning pairs of corresponding points, meaning I've got a point in A and a point in B, and that's a single pair of corresponding points. So the question is, how many pairs would I need in order to figure out the translation? A3, B1, C2, D4. All right, well, the answer is B, 1 point. Because translation is a 1-point transformation. If you tell me where this bottom left-hand corner, better make it bigger, big point, bottom left-hand corner is over here, I know where the rest of the image goes. A couple of ways of thinking about that. One to think about is there's only 2 unknowns. And every pair of corresponding points gives me 2 equations. It tells me how the 2 x's align and the 2 y's align. So each pair of points gives me 2 equations. I have 2 unknowns, so I only need 1 pair of points. Got it? Cool. Quiz 2. 2. My finger's a little slow. 2. Suppose I told you that the transformation from image A to image B is affine. Okay, now you have to go back through a few slides. Remember what affine is. Go ahead. Okay. How many pairs of corresponding points would you need to compute the affine transformation? Same set of answers. A, 3, B, 1, C, 2, D, 4. How many pairs of corresponding points to do the affine? Well, the answer is A, had to go back and see, because it's a 3-point transformation. And as written here, there are 6 unknowns in the affine transform. Okay, it's linear. Each pair of points gives me 2 equations. I need 3 pairs of points, which is what we said before. I could take these 3 points and know where these are, and then everything follows from that. Suppose I told you the transform from image A to image B is a homography. Homography. Your word processor probably doesn't know about homography. Mine didn't. It keeps changing it to photography and other things. Homography. How many pairs of corresponding points would you need to be able to compute the transformation? Same set of answers. A3, B1, C2, D4. How many points? Well, the answer is 4, which is D. All right? Why? Because we have, well, wait a minute. It looks like 9 unknowns, right? It's 3 by 3. But no, you've seen this before. It's only matters up to a scale factor, right? I can scale all those entries in the matrix by a constant, and when I map it back out to the non-homogeneous coordinates, when I divide it out, that scale factor goes away. So there are 8 unknowns, 8 degrees of freedom. Again, I can take 4 points, the 4 points of a rectangle, plop them down here. They don't have to be 4 points of a rectangle, it's just easier to see. And once I've mapped 4 points to 4 points, assuming I don't have any weird degeneracies, then I could compute the homography. What do I mean about weird degeneracies? Well, here would be one. We said that points that start on a line have to stay on a line. So if I took 4 points that were on a line, and then I mapped them to 4 new points that were not on the line, the system should explode, and it would, and your computer would melt and all that kind of stuff, because there is no linear solution of this projection that would map 4 collinear points into 4 non-collinear points. But in general, if I have 4 points distributed spatially, and I put them down, and I map them to 4 other points distributed spatially, then I'm able to compute the homography. Many times through this class, I'm going to ask you, how many points do you need to compute a homography? And I hope at least you'll scream 4. I'm amazed when I do this in class. I say, how many points do you need to do homography? And they don't know, and it's only been like 8 minutes since I did this, so pay attention. Believe it or not, that's the end of this lesson about mapping from image to image. It's a short lesson. I know I needed a break, or you needed a break, or somebody needed a break. Anyway, what was happening was I had these lessons, and they were going on for like 12 hours. And I said, that's probably not good. So in the interest of bio breaks everywhere, we decided that we would shorten some of these. So that ends on sort of image-to-image transformation using the projective transforms. And now we're going to continue our conversation about projective geometry. And it'll get a little bumpy, so, you know, take a breath, we'll charge ahead. The cool thing is, the next thing we're going to do is make serious use of homographies to do something cool that will wow and amaze your friends, assuming you have relatively nerdy and boring friends. Otherwise, they're going to tell you to get out a little bit more often. Anyway, talk to you soon. Welcome back. All right, so today we continue on our tour through multiple views and views, and today we're going to talk about homographies, which we learned a little bit about last time, and a cool thing, mosaics. In particular, last time we talked about a variety of projective transformations, and we said there were some special cases like translation similarity that did not divide out by that last time, but in the general case had 8 degrees of freedom, 8 coefficients, and you did do that division to go from homogeneous to inhomogeneous. And that last one, the one that used all 8, was called a homography, and we're going to use that extensively today. This was the description of projective transformations. For 2D coordinates, it's 3 by 3 applied to the homogeneous, so x, y, w gets mapped to w prime x prime, w prime y prime, w prime, and to go to non-homogeneous or inhomogeneous, you divide through by the w. So now I'm going to do just a little bit of the projective geometry that relates to the homogeneous coordinates we've been talking about, and we'll do that a lot more in the next lesson. So what is the geometric intuition behind using homogeneous coordinates? The bottom line is that a point in the image can be thought of as a ray in projective space. So what I mean by that is, so every point xy on the image plane, let's change the color here so you can see this. So here we have this point, and we're talking about xy, can be thought of as on this ray intersecting an image plane that's at a value of z equal to 1. By the way, and I stole this slide from someone, somebody was very clever here. They wanted positive z to go along the direction of the camera. So you notice they have x this way. This is negative y. So it means positive y is down, and if x to the right and positive y is down, x to y means z goes that way. It was a way of keeping a right-handed coordinate system. don't worry, you will screw this up. That's okay. I just